Following are the steps involved in solving a maximum and minimum problem. Step number 1, draw a diagram. Step number 2, introduce the two variables and define them. Let's say y be the quantity to be maximized or minimized, and x be the quantity that can be varied. 3, form an equation using the known quantity and an equation for the quantity that needs to be maximized or minimized. Now equate the first derivative of the quantity that needs to be maximized or minimized to 0 and then solve for the unknown. And then use the table of test points to confirm whether it's a maximum or a minimum, and the final step is write a careful conclusion. Let's look at this example. Find two non-negative numbers whose sum is 9 so that the product of one number and the square of the other is a maximum. So let's say x and y be the two non-negative numbers such that x plus y, the sum is equal to 9, and if that is the case, then y is actually equal to 9 minus x if I make y the subject of the formula. Now the quantity that needs to be maximized is p, the product of one number and the square of the other. I already know what y is. Y is 9 minus x, so I substitute 9 minus x for y, and I find the first derivative. When I find the first derivative using the product rule over here, I get the first derivative equal to 9 minus x into 9 minus x minus 2x, which gives me 9 minus x into 9 minus 3x. So this is the first derivative. Now I equate the first derivative of the quantity that needs to be maximized, in this case equal to 0, and solve for x. If I do that, and using the null factor theorem, I could say 9 minus x is equal to 0 or 9 minus 3x is equal to 0. That gives me two solutions, x is equal to 9 or x is equal to 3. Now I use the table of test point using the first derivative. The critical values are 3 and 9, so choose values on either side of these two critical values and check the gradient, whether it's positive or negative, whether the function is increasing or decreasing. In this case, to the left of 3, the gradient is positive, in other words the function is increasing. At x is equal to 3, it's 0, x is equal to 4 is decreasing, so therefore at 3 we have a maximum, and at x is equal to 9 it's 0, and x is equal to 10 it's increasing. So at x is equal to 9 we have a minimum. Now the maximum occurs at x is equal to 3, therefore y will be equal to 9 minus 3, which gives you 6. Hence the maximum product will be 3 times 6 squared, which happens to be 108. Let's look at the next example. A farmer wishes to build a rectangular pen for his animals out of 40 meters of fencing. What should be the length and width of the pen so that the area is as great as possible? So let L be the length and W be the width of the pen. We wish to maximize the area, which is length times width, and we know some information about the perimeter. The perimeter is actually 40, so therefore 2L. Since it is rectangular, the perimeter will be 2 times the length plus 2 times the width, which will give me 40. Now in the second equation, I can rearrange this equation to make L the subject of the formula. I get L is equal to 20 minus W. Therefore I can rewrite the first equation for the area using 20 minus W for L. So I get 20W minus W square. Differentiate A and equate it to 0. So I get 20, take away 2, W is equal to 0. Therefore W happens to be 10. Once again, if W is 10, then substituting 10 over here will give me L is equal to 10. First derivative test, if we use the width and width of 10 and choose values on either side of 10, we see that it's positive, so it's increasing. It's 0 at 10 and then it's decreasing, therefore width of 10 will give me the maximum area. Therefore the farmer should build a pen with a width of 10 feet and a length of 10 feet. That will give you the maximum area. Another example, a box with a square base and closed top is required to have a volume of 8,000 cubic centimeters. Find the dimension of the box that will minimize the amount of material used. In other words, we're trying to minimize the surface area. So let L be the length of the square base and h be the height of the box. So the volume of this box will be given by length squared times height, which in this case is equal to 8,000. So if I rearrange this equation, I get H is equal to 8,000 over L square. I got to minimize the surface area, and the surface area of this cube will be the sum of the areas of all the faces, which will be 2L square plus 4 times length times height. And then I can replace this H by this expression over here, 8,000 on L square. Once I've done that, I can differentiate the surface area, the expression for surface area, equate it to 0 and solve for L. In this case, I get L is equal to 20. And if L is equal to 20, I substitute L over here and do 8,000 divided by 20 square. I will get H is equal to 20 as well. Now, just check whether an L of 20 will give me the maximum area, the minimum surface area. So you can see the function to the left, or the function is decreasing to the left of 20. It is 0 at 20, and it is increasing to the right of 20. Therefore, the critical value of L is equal to 20 represents a minima. Hence, we know to have the minimum surface area of 2,400 square centimeters, which you can calculate by substituting all the information in this expression. We can say that H and L of 20 will give us the minimum surface area.